Hello, I am Tirth Shah. I am working in Florian Marquardt's group at the Max Planck Institute for the Science of Light and Friedrich Alexander University in Erlangen, Germany. I will talk about steering sound on topological waveguides with light. Let's look at our primary objective. Consider a patterned silicon chip with a phononic waveguide at its center. We want to shine the laser light at this waveguide. Because of the radiation pressure, it should excite mechanical vibrations, and these phonons should travel along the waveguide. In addition, we want the phonon transport to be robust against sharp turns. This happens in topological transport, so we want to make a topological waveguide for phonons. To attain this objective, we need to come up with the right etching pattern or the right pattern of holes. In our group, we work on theory, that is, we come up with the design of this pattern of holes. And we have a collaboration with Oscar Painter Group at Caltech, who is currently working on the experimental implementation. This field of designing topological waveguides for phonons or photons it's relatively new. It started in around 2013. The primary reason why people are interested in designing these waveguides it's the fundamental physics. Topological physics was first studied in 1980s through the discovery of quantum Hall effect, and later in 2005 scientists proposed quantum spin Hall effect. Topological physics is very well studied for these charged particles. Now people want to apply similar ideas to design these topological waveguides for phonons and photons. So it's basically applying ideas from one field of physics to another field. Another primary reason of why people are interested in designing these topological waveguides is the potential application. Topological waveguides have an important characteristic of robustness against disorder. This can be used to make topological delay lines and topological lasers. Another nice property of topological waveguides is that they are non-reciprocal. That is, the energy can be transported in only one direction and not the other. This can be used to make topological transistors and topological amplifier. Now, how can one design these topological waveguides? Here we take inspiration from quantum Hall effect, that is the charged particle in a magnetic field example. In the presence of magnetic field, the electrons move along only one direction, say clockwise, along the boundary of the material. Here, time reversal symmetry is broken by the magnetic field. In a similar manner, my group proposed a scheme where a laser with the right pattern of phase can be used to excite phonons in only one direction, say clockwise. However, this is difficult to implement in an experimental setup. So, we take inspiration from another well-studied phenomenon, which is the quantum spin Hall effect. In quantum spin Hall effect, because of intrinsic spin-orbit coupling, the spin up moves in clockwise direction while spin down in counterclockwise direction. Here, time reversal symmetry is preserved. Our group has two proposals based on quantum spin Hall effect. They are feasible but still difficult for an experimental setup. So now in this talk, I will describe another proposal from my group which is now currently implemented in an experiment at Caltech. Since we work on theory, we first like to model our design with the toy models. So here we use a graphene tight binding model with nearest neighbor interaction. One can observe nice Dirac cones in the band structure for this graphene tight binding model. If we now use two different sublattices in the unit cell, then the Dirac cones are gapped. This happens In graphene, for example, when we replace one of the carbon atom in the unit cell of graphene with another atom. There is an interesting property of this gapped Dirac cones in graphene. Please note that here we do not break time reversal symmetry, so the Chern number for both the bands is still 0. However, if we look locally at the k or k prime values, one can define a valley Chern number whose values are plus half and minus half. That is why the name valley Hall effect. The total Chern number for each band is still 0. Now, if we make a domain wall configuration, that is, keep the same geometry for gap Dirac cone case in domain 1, the geometry in domain 2 is constructed by interchanging red and blue dots, that is, interchange the two sublattices. Now, if this geometry is infinite in x direction, then we can define a unit cell and plot band structure. We observe topological edge state in the bulk band gap. This edge state is localized at the interface of these two domains, and it travels along left or right based on the slope of the band in the band structure. Let us now see how we can implement this toy model in a real structure of silicon chip. We propose a snowflake crystal, that is, holes etched in the shape of a snowflake, and these holes are arranged in a triangular lattice. In addition, we also have photonic crystal cavities embedded in between the snowflake holes. Remember from my first slide, we want to shine laser light at these photonic crystal cavities. Because of the radiation pressure force, it will excite mechanical vibrations which will travel along the material. The purpose of cavities is to amplify the radiation pressure force by the finesse of cavity, which is around 10 power 5. You can also see how the zoom in of the unit cell with the optical cavity mode looks like. It was very challenging to come up with this design. The major challenges are we need spectrally isolated Dirac cones. We also need our structure to be easily fabricated with current electron beam facility. We need high optomechanical coupling. We also need high optical quality factor of the order of 10 power 5. And one interesting advantage of this design is that mechanical properties are determined primarily by large snowflake holes, while the optical properties are determined by small circular holes. And for our structure, we have coined this term of multi-scale optomechanical crystals. This is unlike the usual optomechanical crystals, where the mechanics and optics are of the same size. For our structure, the mechanics is an order of magnitude larger than optics. We see that our design very closely resembles the graphene tight binding model. We see analogous to graphene tight binding, we also see spectrally isolated Dirac cones in our band structure at 350 MHz. Next step in our recipe was to gap the cones by making two different sublattices in the unit cell. We do that by making cavity holes in one of the two triangles smaller than the other. We observe that this change in geometry results in gapping the Dirac cones. Now we make a domain wall configuration. The domain 1 is similar to the geometry shown in the last slide. Domain 2 is constructed by interchanging red and blue triangles of domain 1. And analogous to our toy model, for the case of an infinite strip in x direction, we can define a unit cell and then we can plot a band structure. We see a topological edge state in the bulk band gap in our band structure, and this edge state is localized at the interface of the two domains, exactly similar to the toy model. So the summary is, we have seen a design of a phonon topological waveguide, which has important properties like it is small micron scale, it has high mechanical frequency of 350 MHz, one can make it on in silicon chips, We also excite and read out the mechanics with light, and we also have a new design of multi-scale optomechanical crystals. We already have preliminary results from our experiment at Caltech, and we plan to publish our results soon. I would like to thank all the collaborators and my funding source, OMT, for this project. Thank you.